this particular lecture is about some, just kind of some posterior, some general information regarding posterior, and also Bayesian model selection. So the Bayesian framework can also be very beneficial for picking particular models. So this is beyond, just finding hyperparameters of distributions. This is also like, what distributions do I even use, right? In the context of deep learning, right? This is like, how many layers of my neural network do I use? This isn't necessarily a Bayesian neural network, but this is the actual construct of the entire neural network itself. Is the idea of Bayesian model selection. So again, we'll kind of go over, so summarizing, we'll kind of go over some same things that we've discussed before regarding, map estimates, stuff like that. We'll go over some intervals ideas. Actually, I believe, well, if he keeps the same homework, this may be one of your homeworks, one of these. At least I remember doing it. And then we may get into some model selection. Won't get fully for this. I don't expect to by the end of the class. Okay, so our posterior distribution, right? So it's the probability of our parameters of our distributions given our data. And basically, in an ideal world, we're able to take this posterior distribution, slap it together with our likelihood, compute this marginal, get a predicted distribution, and then we're happy. However, sometimes that's not possible. Sometimes that's not computationally efficient, so we have to use estimates. And the problem with these estimates, these point estimates, is that sometimes they can lead to overfitting. They can be relatively inaccurate. So they pose challenges. So basically, we're going to discuss some simple quantities that basically can come from the posterior. So this is like, for example, the posterior mean, the map estimate. So right, this is the mode. This is the maximum posterior value, and also like the median. So the posterior mean or median is typically the most appropriate choice for a real valued quantity. However, with the map estimate, right? So the mean or median, or the expectation of the posterior, is not necessarily the map, right? The map refers to the mode. However, basically, the map is sometimes, it's not necessarily the best. So it says here, so posterior mode's AK map estimate tends to be the most popular, and generally this is because it reduces to a optimization problem, right? So we don't actually have to do any sort of inference over, or actual, even with the expectation, right? If we want to do the expectation, finally that expectation, we still have to do an integral. Sure, we can approximate with Monte Carlo, great. But in the context of the map, right, all we have to do is try to find the maximum value, and then that's the best. And that in itself is a lot easier, especially if this is very high dimensional. But as we say here, basically there's a lot of drawbacks with using both. So clearly the most obvious drawback is that it's just a point estimate. So in this case, is that we're losing a lot of potential rich information regarding the actual uncertainty or the shape of our actual posterior. So by taking a point, we're just losing all of that. In many applications, basically it's important to know how much can you actually trust the point estimate. Can we actually estimate how good our estimate is? Basically this is done by specific confidence measures that you can do to essentially kind of give you an idea whether or not the map estimate is good, or if it's not so good, and maybe you should look at doing something a little bit more complex. So here in red, basically, if we don't model the uncertainty of model parameters, then our predicted distribution will be overconfident. This is the same merit as MLE, right? So if we just basically ignore any sort of uncertainty in our model, we say our model, we are positive, it's 100% correct. That's going to lead to overfitting of data, which means that when we predict stuff, it's not going to be so good. So yeah, so this is particularly problematic for, you know, situations where you have some sort of, where you have some risk. And, you know, I mean, this is very important because odds are if you're doing probabilistics, because you're dealing with some application where you want to make sure that, you know, that you're trying to mitigate risks. Otherwise, you just use a deterministic method, right? So here's kind of a very dramatic example here. So this is just kind of showing down here of essentially, this is kind of like, pretend like this is like your fictional posterior, right? So clearly the mode or the map estimate is over here at around 2, but the most of the probability density actually exists closer to 0. So in this case, the map estimate is clearly, it's not a good representation of the actual whole posterior distribution. Yeah, so as it says here, the mean or the median takes the whole mass of the distribution into consideration. And the same is true with the gamma distribution, just the gamma distribution, right? Essentially, you know, you have this exponential decay here, so obviously the mode is going to be way off here at 0, but actually our expectation may exist, you know, down around 2 or between 1 and 2. So yeah, so there's a lot of examples where taking the map may not be very, you know, a value that describes the posterior well. So question is, well, how can we determine, you know, if the map estimate is a good choice, or maybe some other estimate is a good choice? And the idea is basically, well, we just kind of use decision theory, which the idea is that we essentially have like a loss function, and we say, okay, we have some loss, and we want to minimize it, right? So loss will occur if the truth, so if your truth value, and then basically your estimate are basically far off. So if the truth versus your estimate are, you know, far away, not good, your loss increases. So you want to try to minimize the loss, aka you want to make the truth and the map or your estimate value line up. So you can see, actually interestingly enough, that if you take different basically loss functions formulations, right? So if you've done any sort of, you know, kind of optimization processes, these will all look very familiar with to you. But so basically with an indicator function, we see that this type of loss basically it results in the posterior mode, right? So and then down here, the L2. So L2, this results in kind of the posterior mean, and you know this makes a lot of kind of, you know, to some extent some sense, right? You just kind of think like if you know the relation of this, particularly with you know, a Gaussian and also just a general form, and then also if you take an L1, so L1 is just the absolute value, you end up with posterior median. So basically, kind of like what it's getting at is that for a given, you know, a given function or whatever, taking specific measures correlates to taking different types of optimization, different types of loss functions. And, you know, each one of these can provide different information. And, you know, in some cases, maybe, you know, the L1 is the better optimization versus the L2. But, you know, a lot of times, maybe the L2 is the best. So, you know, you know, I can give you an example, right? It's that, you know, if you have a lot of outliers, this one may not be super good. But the L1 may actually be better in this case because, you know, the L1 is a little bit more robust. So basically the median measure may be better than the mean. Yeah, so if you remember, where this kind of comes into play, the reason why we're concerned about map estimate is that we take a map estimate and we plug it into our likelihood, right? Because then that gives us essentially our predictive distribution, right? Is that essentially if we take a map estimate and then we transform it through some function, it may not be exactly what we intended. And kind of it's kind of what we're getting at is that if we take a map estimate and we feed it through some nonlinear function, in this case, like let's just say like it's like our likelihood, right? So we're trying to get the predictive. The likelihood may warp our actual point estimate such that the output distribution, the location of the map estimate may be way off of where we really want it to be. So this is kind of showing the transform of distributions, so change of variables. And essentially what it's saying is that, because it's Jacobian, right, so if we transform a variable, the maximum value of basically p of x is not equal to so the max value of p of x and max value of p of y are basically not equal to each other. So you can't plug in the max value, transform it, and then get the max value of y. That's not guaranteed. And that's kind of like, that's the issue with taking the mode, is that the mode doesn't conserve that. This kind of illustrates the point, I think, a lot better. So let's pretend here that basically down here we have our posterior distribution, so it's like a Gaussian, right? And we're passing it through some nonlinear transform. Let's just say this is our likelihood. So we're arriving on our predictive. And we can see that even if we take, right, so if we take the in this simple example, if we take the mode of our actual posterior and we transform it, we can see that actually this is now basically, it's no longer the mode of the actual the output after this nonlinear transform. So basically this particular quantity hasn't actually conserved between this transformation. Now, if we take a different measure, right? So that's not saying that if we take a different measure, so let's say this is maybe, so it says here that the MLE does not suffer from this issue. So let's say we take the expectation of our posterior, right? Or in this case it's the MLE, so it's the expectation of our likelihood. Basically we see the expectation up here. So this is actually then the expectation of this actual distribution here. So it's not the mode, it's now the expectation, and it looks about right? So we have about equal density on each side, so this would be the expected value. So basically, certain statistical measures, they can pass through certain transforms, and they can be conserved. However, in the case of the map estimate does not. So that's kind of like the takeaway. Here's another, very kind of trivial example of showing basically if we have kind of a very simple distribution of depending on our actual function here. So in this case, it's kind of like our f. Basically, the mode of these two can be very different, even though the original variable that we're transforming is the same. So yeah. So one way to kind of quantify if the map estimate will be good or not is basically by using the Fisher information matrix. So this I. So this is different than the mutual information, okay? So don't get confused. So this link goes to Wikipedia. But basically, the Fisher information matrix is defined as the partial of the log of the likelihood is what this I is. Basically, what we can do is that we can try to optimize this following function. So what exactly is this telling us, right? Well, I can see here is that we have the max data, so I'm going to find the max data that maximize. So this portion here, right? What is this? So this right here is our posterior, right? And what we have is that we have 1 over the square root of this I. So 1 over the square root, so let's just ignore the square root, whatever. Okay, it's going to scale it. So 1 over, and then something that's basically kind of like proportional to the partial derivative of the log of the likelihood. And so kind of what this is saying is that, so if we take an estimate, so let's just say we take an estimate of our data, and then we drop it into our likelihood function, right? So we take a map estimate and drop it into our likelihood. And using that map estimate, our likelihood isn't super good. Okay, so that can happen if your let's just say your prior is super, maybe really informative, right? So what that means is that your data, given the map estimate, your data isn't very probable. So what happens when that's not very probable is you take the log of that, that means your log starts to go, it's close to 0, so probability is close to 0, and your log starts dropping. So you get a really high gradient, right? So what that means is that then that starts penalizing this actual term. So what this is doing is that's saying, hey, I want to maximize my posterior, but I also want to make sure that this point estimate also reflects the data in the likelihood. Because if it doesn't, then that's likely not a good estimate. So basically this is kind of posing kind of another balancing problem to basically optimize around. So kind of interesting. Okay. So now in terms of some switching gears into kind of some more additional analysis regarding posterior estimate and basically estimating parameters is measures such as like interval measures. So the first one we're going to kind of talk about is the credible interval. So the idea here with the credible interval, you've probably seen this, is that essentially this is like, maybe you call this the interval, the credible interval with like, 95%, is, usually the most common. So like, usually on like a Gaussian, if you have a Gaussian, that's usually, plus or minus 2 sigma, right? So the idea with this interval is that basically you're quantifying a region of your parameter that exists between a lower bound and an upper bound. So they don't have to be the same. But when they are the same, basically that's called the central interval. So in this case, you have usually like an alpha divided by 2. So this is like your probability that you're leaving out. So in this case, if alpha is like 0.05, basically that means that on the left side distribution, you go up until the point of where it's 0.025, right? Then you continue all the way until essentially you've hit the point of, I guess, 97.5%, and then basically that's the end of your interval. So there'll be, it's much easier to kind of look at it on a picture, but just think about, you're trying to find the interval of, kind of the highest probability. This can be computed through, Monte Carlo. Something just to kind of make sure to kind of separate here is that so in the context of what we're discussing, credible intervals. So credible intervals or central intervals. This is with regards to kind of the Bayesian mindset. Okay, so that in this case we're treating our model parameters as random variables. Now, if you're into kind of the frequentist setting, so more like the MLE setting, right? Basically, rather than treating your model parameters as a random variable, you're estimating them from data. That's called the confidence interval. So they look very same. They look basically exactly the same. It's basically the setting that they exist is kind of my interpretation. So that's just something to kind of note, is that basically these are not the same. The concepts are the same, but the idea, I guess, really kind of like where they come from is very different. One treats them as the parameters as random variables. The other one basically treats them as basically the deterministic estimates. So I guess this kind of shows you a central interval here, basically the beta distribution. So you can see that essentially I have no idea what the actual interval is, but basically you can the probability density. So the probability density is the area underneath the curve. The area underneath the curve in this portion is equal to this portion, right? So basically this remaining region here is in your central interval, right? So maybe this accounts for, so, right, because there's a probability distribution, it all has to sum up to 1 underneath the curve. So perhaps this is in the previous example, we're doing kind of like a 95% central interval. This accounts for like 0.025. This is 0.025 here in terms of the area underneath the curve, and then the rest is the actual interval. So a different measure that can also be very informative is basically the highest posterior density. And this one is different, and we'll see that this can be very different for basically multimodal distributions, really. Essentially, the idea is that we're trying to find the actual, rather than kind of, so with the central interval, the idea is that we're coming inwards. The idea with the HPD region is that now what we're almost doing is we're kind of operating in the vertical. Is that we want to find the highest probability, right? We want to find the highest probability such that we contain a certain density of the area underneath. So kind of the way to think about it is take this distribution, flip it upside down, and then pour water in. So let's say this is 1, so the area underneath is 1, right? So you have like 1 meter square of water, and now I take 0.95 meters square of water, and I dump it into this, this distribution here. Where that water settles, right, that basically determines my bounds. Okay, and we'll see kind of a picture of that. So that's kind of like what this is saying here, is that, you want the highest probability such that you get, a certain area underneath of the curve. So yeah, so this is kind of showing it here. So rather than, in this case, right, so the central interval, it has the same area underneath here and here, with the highest probability density region, the idea is that we have the same probability for both of basically our interval bounds, right? And yet, basically what this has is that the total area with this bound is the same as this. They're just placed differently, right? And you can see that now these regions, these excluded regions, are then not equal anymore. So it's the minimal width that contains 95% of the mass. So again, kind of think about flipping it upside down and pouring water into it, and then where like the water lies. To an extent, you're thinking about kind of like water lines. So this is kind of showing it here. Basically, you have your central interval. So you can see with a distribution with two different modes, right? The central interval includes basically this very low probability region, right? And then with the HPD region, we actually get separate. We get separate actual intervals. And this is because essentially what we're doing is that we're looking for the highest probability such that we get the total area, right? So it's like the area here, but we still have like the same level. So with this type of setting, like you just have to be mindful is that the HPD region can have multiple bounds, as it says here. Basically, it's not necessarily connected, while the central interval is. So it's two different ways of looking at where in terms of likely estimates exist. Okay. I think I'll just go through this, and then we'll stop at, or maybe we'll do like the first slide of model selection, but I won't go too deep into it. So this is kind of like an example of showing basically kind of an inference example of showing where maybe a confidence interval would be useful. So the idea here is that suppose that you want to buy something on Amazon. In this case, it's like a book, right? And you're trying to, I'm sure we've all done this, right? You go on Amazon and you look and you see, okay, how many 5-star reviews does this one have? How many 5-star reviews does this one have? How do the quantities vary, right? And this happens very frequently, right? Maybe you have one that has 100 reviews, and maybe they have like a 4.5-star rating, and you have another one that's maybe down low on the list, and sure, maybe they have 5 reviews, but they're all 5-star. So it's like, how do you judge which one is better? In this case, it's kind of obvious what you would choose, but this is just going to illustrate of how we can use basically Bayesian inference to kind of deduce that reliably. So in this case, we have seller 1 has 90 positive reviews. It also has 10 negative reviews. And then basically seller 2 has 2 positive and 0 negative. So in terms of just the pure score, we would pick seller 2. However, that would be basically really overconfident because we know there's not a whole lot of data for seller 2. So we can sketch this in kind of like the Bayesian analysis formulation and essentially kind of probabilistically deduce, which one is more probable to actually be the better seller to buy from. So what we do is that we simply have, so in this case this is going to be kind of like a beta Bernoulli type situation here. So basically we have two reliabilities of the sellers. This is basically the transaction, I guess, being good. So it's like an on-off switch. So we have seller 1 is denoted by theta 1, seller 2 is denoted by theta 2. And we say that we have some priors on them, which is basically just uniform, right? So beta with hyperparameters 1 and 1, it's uniform, so it's uninformative. However, like what we know, what we've done before, right? What this is going to do is it's going to allow for some additional smoothing on the actual the estimates on the predictive, which is down here. So the posteriors. So if you remember, assuming I don't have the information here, but assuming the likelihood is Bernoulli, right? And we have beta prior. Beta is conjugate to Bernoulli. So what does it end up being? It ends up being a beta posterior. So we have the posterior on theta 1, and you have the posterior on theta 2. And again, let me emphasize again, we see the +1 smoothing, right? So we have the posterior estimate. So we have 91 positive, and we have 11 negative, right? So what we've done is we added 1 to each kind of observation here. Same over here. So even though seller 2 never had a negative review, by basically placing this prior on it, we've basically accounted for a potential unseen observation. So now basically what we're going to do is that we're going to compute what is the probability of theta 1 basically being better than theta 2. So what is the probability of the reliability of seller 1 being better than seller 2? And we can basically define this as essentially a difference. So basically the difference between theta 1 and theta 2. If it's greater than 0, we know we should pick seller 1. If it's 0, we know they're equal. If it's negative, we know seller 2 is the better option. And then we can see here that, so this is the probability that delta is equal to 0. So this is the probability that we should choose seller 1, right? And in this case, we have the marginal of basically our two posteriors. So we have the posteriors here, and then we have the indicator function. It's basically like just saying, is theta 1 greater than theta 2? If it is, great. Essentially, how do we actually compute this? Well, we would just use Monte Carlo, right? So what we would do is that we have these beta distributions for each one of our sellers given up here. We sample a whole bunch, so we sample theta 1, sample theta 2. Is this one greater than this one? Check. Sample them again. Theta 2 is greater than theta 1. Okay, ignore it, and continue all the way through. And then basically the total number that are greater than, we divide by the total number, and that gives us our probability. So if we actually sample these values, we end up with a 71% that this one will be greater. So basically we know that odds are our seller 1 will be more reliable. So this kind of shows you a more informative view of the actual densities. So basically these are the posteriors on the reliability factors. So you can see that for seller 1, right, it's not 100% because obviously they have have 90 positive, 10 negative. However, you can see that it's very concentrated, right? So it's not very probable that's when we need smaller regions. Seller 2, yeah, it can be, it's probably the mode of it is 100%, that they're 100% reliable. However, you can see that basically it's a lot more, the support region of the posterior is much larger because we have a lot less data. So this is saying that we have a much more vague idea of what the actual reliability of this seller is. So basically, if we do the sampling, so this is like the Monte Carlo approximation of this. So we sampled our betas, compared them, and we just plot. We do histogram, and we just kind of plot them. We know with the distribution looking like this, and we can see that basically. So what the actual what that number is telling you is that essentially 70% of the mass is.
So this is an extremely important topic, and in some way some of the slides contain information that we haven't really covered yet. So I'm going to try to highlight it, and then I will come back to it, especially when we discuss regression models. So what's the idea of model selection, right? There are multiple models that you can use for a given supervised or unsupervised machine learning task. So for example, if you do regression and you feed things with polynomials, somebody can say, what's the order of polynomials? If you use regularization to avoid overfitting, what is the regularization parameter? And many, many other things, as we will see as we go along. So there is a number of parameters. So you can actually think that for different values of the parameters, it's a different model. But you can even go further, right? Let's say if you do regression, I'm saying here polynomial order. So if you use, let's say, polynomials to fit some data, maybe somebody uses Gaussians, or maybe somebody uses splines, or maybe somebody uses kernel methods. So there are many models for the same task, and the question is, which models should you select for a given task? And that's a huge topic in Bayesian calculations that goes under the name of model selection. Now, we already have discussed that if you try to use the training data set to select the model, that's not a good way, because the more complex the model, the better you fit the data, right? So when you do maximum likelihood estimation, you overfit. So what, obviously, as we discussed, what you need to do is you need to have another data set, let's say the test data set, to see what the performance of the model is. Now, I did not mention this before, but often before you go to the test data set, you have what's called a validation set. And in the validation set, maybe you optimize different hyperparameters that you did not bother to compute during the training process in your algorithm. So in the validation set, you optimize hyperparameters, okay? And once you have done that, then you can go to the test data set, and then you can see how good is the predictive capability of the model. So I'm just summarizing on the bottom the three data sets: training, validation, and test. Sometimes people don't do any validation, maybe they don't have any hyperparameters, and they directly go to the test data set. So today I'm going to teach you actually how you do Bayesian model selection, and that's not an easy topic, okay? I mean, actually it's not very complicated, but it's different, so we're going to have to sort of pay attention on how things are happening. Now, before doing that, let me remind you that the non-Bayesian way to do model selection is cross-validation. You remember what's cross-validation, just in spirit? So based on this picture, what is the idea? So what we have done here, this is all of our data, and we split it in 4 pieces. So what do? Like if I look at run 1, so we're using 3 of these pieces of the data to do the training, and then we do on the first piece, we do the testing. Then we use this to do the testing on the second run, this on the third run, etc. And then we average the performance of the model. So that's the cross-validation methodology, and in this case is a 4th-fold cross-validation. It's a non-Bayesian way for actually, figuring out the performance of the model, but even some Bayesians are using it, because some reviewers are accustomed to cross-validation, so they say, please do that as well. So the Bayesians don't like doing cross-validation, because if you look at each of these computations, right, it's like the cost of the calculations is 4 times as if you use all the data set at once. So you're repeating this 4 times. That's one thing. And the other thing is, in, let's say, run 1, you're using 3 pieces of the data set, and you don't use the 4th to train the model. The Bayesian way of doing things is, you have the data set, use all of it for training. Don't split it in training and testing. Use all of it, okay? But this is what this cross-validation is all about. Okay, now, let me throw this slide a little bit ahead, and I will come back to actually prove this by the end of the lecture today or on Thursday. So, we said that doing maximum likelihood estimation, right, is, or fitting to the training data set is not appropriate because the more complex the model, the better you fit the data. So somehow people in the 60s, they said, well, okay, so we don't want a model that is very complex. So how about if we maximize the likelihood of the data, but somehow also penalize the complexity of the model? So fit the data as well as possible, but don't allow models that they are very complex. So they came up with different criteria, and we will see a systematic way of deriving this in a Bayesian way. So I am not saying anything on that yet. But one of these is the Akaike information criterion. And I wanted to throw it because it looks like this. It says, select, let's say, the parameters W of the model so that you maximize, what is this, the first term? Say it again. That's the log likelihood, right? So that's the log likelihood, and M is, let's say, the order of the polynomials that you use, right? So it's the complexity of the model. So it says, yes, fit the data as well as possible, but at the same time, keep the complexity what? How do you maximize when it's minus M? So M has to be as small as possible, right? So you fit the data as well as you can, but at the same time, you have to minimize the complexity of the model. So one way or another, all the criteria that are being used to select models, we will have some form of log likelihood minus something that accounts for the complexity of the model. And we're going to derive them in a very principled Bayesian way. As a matter of fact, this criterion, the way that you see it here, it's empirical. Even though it was used a lot in the 60s and the 70s, there is no Bayesian formalism of this. Again, I just want to give you this right now so that you start thinking on what the objective is. If you want to select a model, you want one that is not very complex, all right? That comes from this term, but at the same time, it fits the data as well as possible. Okay, so if you maximize the first term, you overfit. By controlling down the complexity, hopefully you will do much better. Okay. All right. So I don't want to go on this slide. There is nothing. So let me be futuristic now, and the notation here is. We have to pay attention, okay? So let's assume that we have many models, and I'm going to denote these models with a little letter m. Okay? So, m equal to 1 is one model, m equal to 2 another model. Each model can have its own parameters. It can be of completely different nature, but we denote each model with m. And let's say that I give you some training data set D. All right? So what this equation is about, can you look at it and tell me what it gives me? So look at this equation and tell me what this equation gives us. What is on the left-hand side?
Posterior.
The posterior over? It's not usually when we talk about Bayesian things up to now, right? We talked about the posterior parameters. This is not the posterior over parameters. This is the posterior over. It says P of M given D. So what is that? What is M? The model. So it's the posterior over models. So the idea here, every model explains differently the data, and we can compute a posterior over models. Okay? And you notice when you look at this equation, the parameters are not there for each model. Why? Because the parameters have been integrated out. And we will see how to compute each term. So the idea here is the posterior over models is what? The likelihood that model M can explain the data D. That's the prior of the model M. And at the bottom, you have the normalizing factor that we get in this Bayes theorem, if you like. Okay? So this is the posterior of models. Let's say that we can compute this posterior over models. All right? How? I already actually highlighted this in the beginning of the course in the introductory lecture. Let's say we can actually compute this. Can you tell me, if you already have all of these posteriors, which model will you select in a Bayesian way? I mean, what will be the obvious choice of a model? The one that maximizes the posterior, the one that has the maximum P of M given D. Okay? So you will select a map, basically estimate. So you will select M bar, which is the M that maximizes this posterior. Now, I have to tell you that doing this calculation is not going to be easy. Okay? But if you do the type of calculations implied by this formula, effectively you're not doing Bayesian calculations. I mean, Bayesian things start with this type of calculations. Okay? So, and again, I remind you, the parameters are not shown explicitly. They are integrated out when you write this formula. So this formula is the posterior over models, and every model has its own parameters. So we are going to compute this. We're going to have to discuss on how to compute the likelihood of the data for each model. All right? So before I actually give you the equation on how to compute this, so this is the likelihood of the data under model M. So let's forget M for the time being. Let's say that we work for a particular model, M equal to 1. All right? So what is this quantity in the numerator? P of D for model 1. What is that? Can you tell me one formula where we maybe have seen P of D? So if you take, let's say, model 1 that has some parameters theta, and you write the posterior of theta, how does the Bayes rule looks? The posterior of theta given D is the likelihood, which is the probability of D given theta, times the prior P of theta. And what do you have in the denominator? P of D. So this is the normalizing factor, this P of D given M, right? For each model is the normalizing factor that we have seen in Bayes' rule, and we did not really bother up to now. So the normalizing factor comes to be the key ingredient to actually do model selection. You will see the formula shortly, right? But this is what we had as a normalizing factors when we wrote the posterior parameters for model F. Okay, so actually, there is this equation. That's the normalizing factor. Look at it and tell me, I mean, obviously, if you think of the posterior of the parameters, right, and the normalizing factor, this is what you get. But can you actually tell me a half a line derivation of this equation? So suddenly, on the right-hand side, I have introduced the parameters theta. So how do you get this? How do you go from this to that? Right? So I have the probability of D given M. So let's forget M actually, right? So, we select what M is. So we have P of D. So you know what? I can write this P of D as P of D comma theta, integral with on theta. Can I do that? How do we call that rule? That's the marginalization rule, right? It's the sum rule of probability. I can write P of D as P of D comma theta, d theta integral. Okay? And then I have the joint distribution of D and theta. And how can I write this as P of D given theta times P of theta? And which rule of probability is that? The product rule. All right? The product rule. So somehow now we brought out these parameters for the particular model M. All right? So this marginal likelihood for model M is written as the product of the as the integral basically of the product of the likelihood for model M times the prior. Pay attention, you may want to take a note. You remember when you write the posterior of the parameters, you have likelihood times the prior. So this term there is not the posterior, it's the prior of the parameters. This is very important, it's the prior, not the posterior. All right, so this quantity that you see here is called the evidence for model M. I mean, in principle, is a marginal likelihood, marginal because we have integrated the parameters theta out, but the common name that we use in machine learning is the evidence for model M. I mean, it's basically how well model M explains the data D, okay? And it's marginal likelihood because it does not involve the parameters theta. As you can see, this equation have been integrated out. Okay. All right, so I'm just gonna go back now, all right? And look at this equation, okay? So this is the marginal likelihood or the evidence for model M. Okay, so let me just go back to this equation so I can ask you a question here. So when you look at this equation, right, this is the posterior of model M, and it is the marginal likelihood times the prior for model M times this normalization term. When you do this calculation here and you select the model that maximizes the posterior over models, in principle, it is almost the same as maximizing the evidence, in particularly when the priors on each model is a uniform prior. So if you assume that all the models have the same prior, right? So all of them are having the same prior chance of explaining, you start with P of M being a uniform distribution, you can see that maximizing this is the same as maximizing the evidence. So let me ask the following important question. If you maximize the evidence, which is P of D given M, so if you maximize this evidence here, do you overfit? In other ways, by maximizing the evidence, will actually the procedure select the model that has the highest number of parameters, the more complex model, or not? You remember maximum likelihood, right? So when we try to just fit the training data, it says make the model as complex as possible because that fits the data best. So I am asking, if we try to maximize this, will it actually select the most complex model or not?
Yes.
Huh?
Yes.
Yes? So the answer is no. The question is why not? And this is extremely important, and that's where this Bayesian formalism comes. Why maximizing this evidence will not give you the most complex model? There is something in that equation that says that is not going to happen. you know what? The parameters theta have been integrated out. So it doesn't matter if I have 5 parameters or 5 million parameters, because the evidence doesn't depend on how many parameters I have. The parameters have been marginalized out. So this thing avoids overfitting. And that's why evidence is the way basically to select models in Bayesian type of calculations. Okay, so
I think it doesn't penalize for the number of parameters.
well, we are going to come to penalization, and you will see this. But maximizing, so if I take a model again, right? If I make this a uniform distribution, so P of M doesn't come in the picture, and we try to find the model M that maximizes this posterior is the same as maximizing the evidence, that evidence does not have any issue with overfitting because the parameters have been integrated out. Okay, I am going to show you approximations on, and when you see the final formulas, you will see how the penalization of the complexity of the model comes out. All right, so we will hopefully do this today. All right, so so it says here if we integrate the parameters out, rather than maximizing them, and you maximize the parameters when you do like maximum likelihood estimation, right? This is fitting the data basically directly, okay? We are protected automatically from overfitting, and this is the same thing as the Occam razors principle that we have seen before, okay? So this thing will actually select simple models, and we will see how. Okay, let me put an analog. Okay, and this is with some stretching. I don't know from where I got this analog. Maybe there is a reference on the bottom. But just to give you a vague relation of maximizing the evidence with cross-validation. I mean, the two things are unrelated, right? Because one is a Bayesian, the other is a non-Bayesian. But let's see something that maybe it can help you to realize how this evidence comes about. Let's call all the data that I have collected as y1, y2, y3, yn. Can I write the evidence for a given model like this using the rules of the product of probability? That's an exact formula. Can I do that? Right? Right? It's the exact rule of the product of probability. So, you know, if you look at this formula, it says to calculate the evidence. First, you compute P of y1, so it's the margin of y1, and then it's P of y2 given y1. And I want you to tell me how that may relate with cross-validation. In cross-validation, what do? We take a training data set, a part of the data, so in this case y1, and then we calculate the performance on another data set. So P of y2 given y1 looks like doing cross-validation. And then similarly, we fix here y1 and y2, and we evaluate how well we do with y3. So if you can, I mean, when you do cross-validation, right, you can immediately see, let me go back. If the model is very complex, we will overfit these early probabilities like P of y2 given y1 and then P of y3 given y1 and y2. So as you keep going to compute the evidence, all right, the calculation is going to be a very bad one. Okay? So there is somehow an analog between model evidence and the ideas of cross-validation, but again, cross-validation is a non-Bayesian setting. P of D comes directly from Bayes' rule. So we're doing this with some stretching, but you know, you can maybe get some insights that way. Okay. So let me address the following problem so we can be very specific. Let's say that I give you two models, M1 and M2. Model M1 has parameters θ1, model M2 has parameters θ2, and I give you some data set to train the two models, and I ask you which model is the best. All right? The first point that I want you to make clear is you cannot say which model in this setting is the best alone. You can only compare it with another model. It's very important. So I cannot say P of M1 is the best, M1 is the best model. I can say M1 is better than M2. And you will see shortly. We can only compare models. All right? We can only compare models. So let's see how this thing goes. Let's work with the model MI. All right? So I can be 1 or 2. Okay? For the model MI, look at this equation. And don't get confused because I use pi and f here. The term on the left-hand side is the posterior of x is my data set. So we have changed this to d, but x is my data set. So theta I is the p of theta I given x is the posterior of the parameters of the model I, and that's equal to the likelihood. All right, I write the likelihood like that. That's the prior, and that's the normalizing factor, which we call it the evidence of model I. All right. So this is the posterior of the parameters. And so from data we go to the posterior, and see now what I'm going to do. If you compute the posterior including the normalization factor, then applying Bayes' rule to the model MI directly, I can compute the posterior of the model MI. So the posterior of the model MI is the marginal likelihood, which is this term on the bottom, times the prior of the model MI divided by P of x. Now P of x is another marginal likelihood, but there is not a model there. It's an average over all models. So P of x on the bottom is what you see on the numerator with a summation on I. And actually I'm not going to bother about P of x. It's not going to come in our picture. Okay? So again, Bayes' rule for parameters gave us this equation that we have seen with different notations before. Now we calculate this marginal likelihood for model I, and then I use this to compute the posterior. All right, so let me do the following calculation. We already said, all right, look at this. What is this thing on the denominator? This thing on the denominator is the normalization factor of this posterior of the parameters, which means is the likelihood times the prior with the parameters integrated out. We agree? We agree that the marginal likelihood is the integral of what you see in the numerator, right? So that's the marginal likelihood. I gave you the formula before, okay? And here's the final result. I am going to compare the posteriors of two models, all right? The posteriors of two models. And the posteriors of two models, if you write this for model 1 and you divide the same thing by model 2, the P of x is going to cancel out. And what you get is, you get the marginal likelihood for model 1 times the prior for model 1 divided by the marginal likelihood for model 2 times the prior for model 2. And then I write this marginal likelihood or evidence explicitly times the product of the priors of the two models. What you see inside the brackets is what is called the Bayes factor. Okay? Is basically a ratio of the marginal likelihoods of models 1 and 2, and together with the priors will give us the ratio of the two posteriors of the models M1 and M2. And I'm going to give you a statistician's point of view. If you can do this calculation and you compute these integrals and you put some priors on models M1 and M2, I am going to tell you, depending on what values you get here, if you select model M1 or you select model M2. Obviously, if this ratio is way bigger than 1, which model will you select? model 1, all right? But somehow you need sort of to be very conservative, right? As engineers we say, you need to put a factor of safety there. And the statisticians have a factor of safety that tells you precisely when you should be confident that model 1 is better than model 2. So I am going to give you actually, let me just actually go to the table, and then I'm going to come and do the 2 examples. All right? So here's the table. If you compare, if you have 2 models, and I'm actually using here a statistician's notation, and I call one model the null hypothesis, M0. So this is like, again, one model we call it M0, and we have an alternative hypothesis we call M1. So this is the Bayes factor comparing model 1 with model 0. All right? So this is so when you calculate the Bayes factor, all right, if the Bayes factor is greater than 100, then you say there is a decisive evidence for M1. If the Bayes factor is greater than 10, there is a strong evidence, moderate evidence, weak evidence, etc., etc. But you notice it's not sufficient if the Bayes factor is just like close to 1, bigger than 1, the evidence for M1 is weak. You really have to go to very high values to say that you're highly confident. So it's like having a factor of safety of 100. Okay? And you may say, why is that? Why do I sort of, need these factors? Because you can realize, right, that there is a lot of things we have done in deriving these formulas. Okay? And there is something even actually, I'm going to emphasize this through an example with a coin toss problem. You notice it's easy to say if the posterior of M1 is bigger than the posterior of M2, obviously model M1 is the one that I should select. But notice the following. The ratio of the posteriors is this Bayes factor times the ratio of the priors. And you know that the selection of the priors is very subjective. You put whatever you like there. So if you go and you calculate the Bayes factor and it comes to be greater than 1, I can select this ratio of the priors anything I want to. So even though this is greater than 1, I can make this ratio less than 1. Right? So somehow you want to put a safety factor to the Bayes factor if you're going to use the Bayes factor alone to decide which model to select. Right? Because the effect of the priors, the selection that you do for these priors, will completely change the ratio of the posteriors of the model M1 and M2. So let me do one example. So we're going to do the coin problem. Right? So theta is the probability of heads. So we're going to do the following 2 models. One model will be that the coin is fair, and we're going to put a prior that's a beta distribution with parameters from 100 to 100. And the second model is that M2 is unfair, and we're going to put a prior that is B 0.5, 0.5. And I think earlier in the introductory lecture, I gave you the plots of this. All right, so you can imagine one prior is more diffuse, and another one is basically puts a higher probability either at theta equal to 0 or at theta equal to 1. But so here we have a model that is a fair model and a model that is unfair. So let's say you collect data that says 2 heads and 3 tails. And you want to decide is the coin a fair coin or it's an unfair coin? We understand the setting, right? So you have to basically put 2 priors, one for the fair coin, one for the unfair coin. Okay? Obviously you need some data. We select 2 heads and 3 tails. And now we need to do a calculation and figure out if based on this data, if the coin is fair or not. I mean, we need to make a decision. obviously, looking at the data set, right, alone, what do you think the coin is? Just looking at the data set. I mean, if you throw this coin 5 times, right, and you get 2 heads and 3 tails, what are you going to say, most probably? How does it look?
Fair.
Fair, all right? I mean, if it was unfair, you're going to get like 5 heads or something, or 5 tails, you know. But no, this looks a fair coin. So let's calculate first the Bayes factor. You need to get used to these calculations because this problem looks like a toy problem, but when in real machine learning algorithms you do model selection, you're going to have to do the same procedure, and the formulas are going to look complicated, but the procedure is identical. All right? So remember, what was the ratio of the Bayes factor? Was the marginal likelihood for model 1 divided by the marginal likelihood for model 2. So this is the likelihood, that's where the parameters come from model 1, the likelihood for model 1, likelihood for model 2, and we said that these are not the posteriors. What are they? They're the priors, right? The priors for model 1 and model 2. All right, can you tell me where did this thing come from? The first term, theta squared 1 minus theta cubed. What is that? Is the likelihood, right, of having 2 heads, 3 tails, yeah, for the Bernoulli distribution for the coin toss problem. And where did this come from? Theta to 99, 1 minus theta 99 divided by the beta function 100, 100. What is this? That's basically the prior, right? You remember the beta distribution is theta to a minus 1, 1 minus theta to beta minus 1. All right? So that's the prior 100, 100. You have to remove minus 1 in the, in the exponent. All right. Can you actually tell me how you're going to compute these integrals in 2 seconds without having to do any calculations? So the beta functions are tabulated in the computer, all right? You can go to Mathematica or something like that, and you can calculate them. And how are you going to calculate these integrals in theta? In principle, we have done something similar. If you combine the theta terms, you're going to get theta to the power 101 times 1 minus theta to the power 102, right? So when you have integrals of the form theta to some power, 1 minus theta to another power, an integral in theta, what does that remind you? This looks like a beta distribution integrated out, so that integral in theta, what is it going to give you? It's going to give you the normalizing factor of the underlying beta distribution. All right? So actually, can somebody tell me what is the beta function that you will get when you integrate this? This is theta 99 and 2 is 101. So what do I get? What will be the first coefficient on the integral when you normalize this? Theta 99 and 2, you get 101. So it will be beta of 100. And then you see 99 plus 3, you get 102. So beta 100, 101. All right? Now, you do the same thing in the denominator, but let me just say, what we just described with words, we can see that this ratio of the evidences of this evidences for models 1 and 2, at the end, when you calculate them, they involve ratios of normalizing factors. I am going to formally do this precisely, okay, for the very general case, but what I described, right, getting in normalizing factors, these are the normalizing factors from the priors, and literally what we got, let's say in the numerator, is we got a normalizing factor basically coming from the likelihood times the prior, okay? And so basically that is, you know what it is? It's the normalizing factor of the posterior. right? Now, you may say, I don't really care, I'm just going to go and compute it, but you will see when things get more complicated, it's important to remember that you'll be getting eventually ratios of normalizing factors. So I'm going to come back to this. All right, so when you calculate this integral, for this case, you get this, all right? And actually, if you want to calculate now the ratio of the posteriors of the modules M1 and M2, would be the Bayes factor times the ratio of the priors. This comes to be 2.58 times the ratio of the priors. And you notice again, if you look at the Bayes factor alone, right, you cannot with confidence say that model M1 is the best, because in this calculation, the ratio of the two posteriors depends highly on the ratio of these priors on models M1 and M2. And these priors for models M1 and M2, I can put literally anything I want, and I can sort of, you put your own priors, I put mine, and then this will change completely this result. So that's why the statisticians like to make a decision for selection of models looking at the Bayes factor regardless of the ratio of the priors, but they put some safety factor. So this number has to be very high basically to say with confidence that model M1 is the best. But in this case, I mean, you can see that the evidence we have, because this is greater than 1, is that these results are coming from a fair coin. If I change the data and I repeat the same problem, by the way, so if we have data of 5 heads, you obviously anticipate that the calculation will give you an unfair coin, or will point to an unfair coin. And indeed, when you calculate the posterior, this number comes to be 0.13. Okay, less than 1. So this is the table that statisticians use when it comes to the evidence that you have for which model is the best, based completely on Bayes factors. So you actually may want to refer to this table, because if you write a paper and somebody in machine learning with good statistics background reads it, you cannot say the Bayes factor is greater than 1, so there is evidence that model 1 is the best, because the evidence, as you can see, is very weak. So if you have decisive evidence, the Bayes factor has to be very high. Okay. Let me do, I don't know if there is anything different to this example. So we're going to assume the following. Again, we continue with the coin example. We're going to take a fair coin. The null hypothesis, or model M0 here, is that theta is equal to 0.5. All right. So I have an equal probability of getting heads with getting tails. And then I'm going to take a biased coin where theta can take any value from 0 to 1. Okay? So theta, I don't know what happens with my nice pointer. So theta can take any values theta can take any values from 0 to 1. Okay? So would you agree with me that the likelihood, the marginal likelihood for the fair coin, if I collect 10 data points, is 1/2 to the power n? Naturally, before I came to the lecture, I was scanning to see what the lecture is going to be today. I looked at it and I said, oh, this must be wrong. Because I'm going to put the formula that we had for this calculation of the marginal likelihood. So this is for model M1, right? But this is our general formula. Okay? So we do know for the fair coin, this likelihood will be 1/2 to the power n. Because every time you see heads or tails, the likelihood is 1/2 and 1/2 and 1/2, right? So 1/2 to the power n, but then there is a prior here and an integral. All right? But you notice the fair coin can only take one value, which is theta equal to 0.5. All right? So if I'm going to do this integral for the fair coin, this prior here is a delta function. Is a delta function like delta of theta minus 0.5. So the integral basically disappears, and you get this whole calculation for model M0 is 1/2 to the power n. You don't have to do any integration because theta can only take one value for the fair coin. Okay? For the unfair coin, all right? So for the unfair coin, you're going to have the likelihood, all right, times the prior, and then integrating theta. So I give you the answer, and I want you to tell me where is the result coming from. Try sort of, use your, so I'm using, obviously, I am going to use a beta prior, all right, as we have done in the previous examples. And the prior is going to have parameters A1 and A0. So I'm going to use a beta prior. And this is, a Bernoulli distribution to calculate the likelihood. So if I get 1 point, the probability of heads is theta. If actually, since we already have done this, right, in an earlier lecture, if I do n tosses of the coin, and I get n1 heads and n0 tails, what is this likelihood? Is theta to what power? To n1 times 1 minus theta to n0. All right, where is this thing coming from? I mean, I can see this comes from the normalizing factor of the prior, right? That's my beta function. Where this beta function comes? You remember the posterior? When you throw the coin n times and you get n1 heads and n0 tails, what is the posterior that you get? You remember conjugate prior, right? If the prior is a beta, the posterior was coming to be what? A beta with parameters alpha 1 and n1, alpha 0 and n0. So you're going to get a beta distribution here, but without the normalizing factor. So when you integrate in theta, you will actually get the normalizing factor of the beta distribution that you see up there. You're going to have to go home and look at it carefully, right? But literally, there is no calculations to add in between because the calculations are in this equation. So if this is, this product of prior and the likelihood will actually give you a beta distribution, but it's unnormalized, okay? And that beta distribution has parameters A1 and N1 plus A0 plus N0. Remember, you add the counts from the prior and the likelihood. And because you have an integral, that integral of a beta distribution will be the normalization factor of the beta distribution, which is a beta function. So the ratio, so basically to calculate the evidence for this non-fair coin, you can see that the evidence is the ratio of two normalizing factors. Is the normalizing factor basically here of the posterior divided by the normalizing factor of the prior. Okay? Now you may say, I have the evidence, and you told us we have to select a model that maximizes the evidence. So effectively, it's like telling you that even the hyperparameters that you see here, A1, A0, need to be selected so that this ratio is maximized. And you may say, how do I do that? Well, somebody already has done that for you. It's in the literature. Okay, and we will maybe come back to this problem, but this already has been done because it's a very common type of calculation that comes in many machine learning algorithms. All right, so let me, so for this example, so we throw a coin, right, and we collect the number of heads in 5 tosses of the coin, and you can see here I get 0 heads or 1 head, so 2 heads or 3 heads or 4 heads and 5 heads. And what I am plotting is, I am plotting the log of the evidence for the unfair coin. All right? So it's the log 10, all right, of the evidence for the unfair coin. So basically what I am plotting is, I am plotting this versus N1 plus N0. Okay? So this is what you see here. Now, I did the calculation actually just before I came. And so let me go to slide 37. If you do the calculation of the log of the evidence for the fair coin, the value actually for the log comes about minus 1.5. So I'm going to draw a line here, all right? Minus 1.5. Okay? So can you tell me, for the different regions where I get 5 heads, 4 heads, 3 heads, 2 heads, 1 head, if for the fair coin I'm there, can you tell me what is the evidence pointing for the different regions? Which hypothesis seems to be explaining the data best? So let's look at when I have 0 heads or 1 heads only in 5 trials. With the evidence for the fair coin being here, which one do you think is the correct hypothesis, the fair or the unfair coin? Which one has the maximum marginal likelihood? It's on the log scale, but don't be bothered, right? So this, again, total counts, right? So I have 0 heads here, and the fair coin, the line's here. All right, so you can see when I have 0 counts, the log of the marginal likelihood for model M1 is very high. It's there. Then I have there. But then when I go to 2 heads or 3 heads, all right, you notice the fair coin is there, so it has a higher evidence. And then again, on the other side, the unfair coin has a higher evidence. Does this make sense? I mean, forget the evidence, right? When you somehow, when in 5 tosses of the coin, you only get 0 heads or 1 head, what are you going to say? Is the coin fair or not? It's not fair. And that's exactly what you get, because if the evidence for the fair coin is here, the log evidence, right? You can see that the evidence for the unfair coin is higher. And when you get 2 or 3 tosses, the evidence of the fair coin is higher, but it makes sense, right? If you get 2 or 3 heads in 5 tosses of the coin looks fair to me. And so that's looking at the evidence, but if you want to look directly, you actually have it, I think, on the next slide. This is the exact calculation of the evidence, and what you see on the right-hand side is an approximation of the evidence using what's called the Bayesian information criterion. So I'm going to wait until I reach that point to introduce what the Bayesian information criterion is. But the idea is, if you don't want to do the integrals to calculate this evidence exactly, you can do an approximation that is called BIC. And that approximation, the plot that you get, in principle looks very similar, you know, and it gives you the same answers as the exact evidence calculation. So I'm going to come back to what this plot is. I think these are the same results with another computer program, or it's my results basically, and the other one was cut and paste from Murphy's book in chapter 5. Okay. This slide is a little bit complicated, so I am not going to go through it. I am going to say, you can actually read it. It has all the information that you need, okay? I am going to say the following. When you compare models, right, so you can select which model is, if M1 is better than M2, you need to be very careful to use what is called proper priors. So you cannot actually have a prior that says, oh, you know what, everything is possible, all right? So take a uniform prior, right? So if you actually use improper priors and you follow the calculations, you can see that in computing the Bayes factors and the posteriors of the different models, you can get any results you want to. You get basically all garbage. So the idea here is, if you're going to be doing model selection with Bayes factors, you have to use, and this is for the parameters, right? I forgot to say, this is not for the models. This is for the parameters. You have to use proper priors. And maybe right now, the word proper prior doesn't mean very much, but we will see when we do examples, even in regression models, you will appreciate what a proper prior means. So you can think, again, a uniform distribution of the parameter theta, that would be improper. Because what is the integral of a uniform distribution if you integrate something? Let's say I give you the value of, the distribution is constant equal to 5. All right? What's the integral of that in the parameter space? If you allow parameters that go from minus infinity to infinity, and you have something that's a uniform distribution, what's the integral? It's infinite. So you cannot normalize it. All right? And so that's why one way to think of improper priors. But another way to think of improper priors is to take a Gaussian distribution where you allow the variance to go to infinity. So it's a very open Gaussian, right, that tries to approximate a uniform distribution. So even in that case, you will ruin the calculations that we have done for model selection. And this goes under the name of what's called the Jeffreys-Lindley paradox. Okay? Effectively, don't use improper priors when you do model selection. And again, this slide does some simple calculations. If you read it, you will appreciate what we're talking about. Okay. Now I have 3 slides. They're the same slides, actually, the same picture. And they contain an extremely important concept that I want you to understand it. Okay? So we're trying to select models, right? So let's say that I have, here, I have 3 models, all right? This is, here I'm showing actually 2 models, M2 and M3. And I have some data that I call them D0, all right? So I want to figure out which model should I select, model M2 or model M3. Now, this picture is a little bit, requires your imagination, right? In mathematics, you have to imagine. So when you have a model, I have not given you any particular data set. So the question is, can the model explain different data sets? So what you see on the horizontal axis, you see all the data sets that you would like to be able, a model to explain. All right? So somehow on my horizontal axis, I put different types of data sets. Okay? So what you see here is, for each model, you see this is the evidence. All right? This is what we discussed before, is the marginal likelihood. But effectively, we are trying to, what you see in the plot here, is the probability for a given model to explain a given data set. So can you tell me, for the data set D0, how well this yellow model M2, let's call this, how well this model explains this data set D0? What is the probability that this model assigns to the evidence for this data set D0? If I look at the yellow model. So when you look at the yellow model, right, it peaks and then it drops down to 0. So the yellow model cannot explain any of these data sets. It assigns very small probability. So you can think a model that is very simple, right? A model that is very simple cannot explain all the data. So in this particular case, it assigns to the data set D0 a very small probability. Is this model, this yellow model, a simple model or a complex model? I mean, you notice it only explains a few data sets. So is it a simple model, you think, or a complex model? But it only explains a few data sets. I mean, if I have like a 50-order polynomial, you can fit anything you want to. So this cannot explain data at d0. So it has to be a simple model. So the simple model, what it does is, it assigns very high evidence, very high probability to some data sets, but it cannot explain many other data sets. And why is that? Because there is conservation of probability. If I take a particular model and I compute this, and I sum for all possible data sets, this has to sum equal to 1. So a model is trying to explain different data sets, right, and assign a probability to each data set, but the sum of all of these probabilities has to be equal to 1. So in our case, the probability assigned to d0 is very small, and the probability to all these data sets here is very high. So that's a simple model. If you look at the red model, what is the probability it assigns to d0? It looks to be a serious probability, right? So way higher. And also you can see that M2 can explain more data. Can you see that? So what is the complexity of model M2 versus the yellow model? Is it more complex, less complex? What is it? More complex. So I may call the model M2 an intermediate complexity model. And now let's look at the blue model. What does the blue model do? It's a very complex model. It can explain a lot of data sets. But based on the probability conservation equation that you see here, if a model can explain many data sets, the probability it assigns to each of the data sets is what? It has to be low. Okay? So basically, you can see now this Occam's razor approach, right? That the right model is one of intermediate complexity, and this picture contains the spirit of what we discussed, right? And you will see this picture literally, and I'm copying this from the ICML conference from a paper of Zubin Garamani. Many people, even today, that give presentations on different topics, they use this picture because it is relevant to anything in machine learning. Okay? It explains this interplay of fitting the data versus the complexity of the model, and it's all about the picture that you see in here. Okay? So let me, again, we haven't done anything for regression, and if I understand, in your previous computation statistics course, those who took it, the professor didn't cover regression, right? Is that correct? So we're going to have to go back and spend a week or two on regression models. But let's say somehow we already know how to do regression, okay? We don't really know, but let's say we know. So we are given 3 models. The simple one, right, that fits this data, that's a straight line. The intermediate complexity, that's a parabola, and maybe, I don't know, a 10th order polynomial that fits all the data sets. Okay? So actually, you know what, when we do regression, literally we're going to calculate the evidence, and we're going to do this selection of the model precisely for regression models. But right now, I want you to see the analog of what I was describing here and I was describing there. I mean, the straight line can only explain a few data sets, all right? The M2 can explain this particular data set better, all right? And M3 can explain a lot of data sets, right? You can make it to fit in many data sets, but the probability assigned to each of these data sets is very small. So the correct model in this case would be M2, but if you want to formally do this and prove that M2 is the best model, you're going to have to actually show that the evidence of the data under model M2 is the highest. And we're going to have to calculate that evidence when we discuss regression problems, but I think I'm going to show you a schematic of that. All right, so here it is. So don't ask me you know, how I got all of these curves and from where they came, because we will revisit this exact slide and the methodology when we discuss regression. So let me just tell you what is plotted. These points are my training data. This line that you see here, I call it a yellow line, is the exact generating function for the data plus some noise. Okay? And the Bayesian regression model gives me the following results. It gives me a mean value for predictions that you see with this red line. And these dotted blue lines are the predictive uncertainty, plus minus 1 standard deviation. Again, the details are unimportant right now. Okay? So somehow you do predictions with a regression model fitting different order polynomials, and this is what you get. So I am going to read the results here. It plots the log evidence, all right? And this is for a model that is linear, a straight line, b equal to 1. And the log evidence, if I can read it, is minus 18.899. Here you fit a parabola. The evidence is minus 20 on the log scale. And here you fit d equal to a cubic polynomial, and the evidence is minus 21. So which model has the biggest evidence for this data set? From the three numbers that I read you, which model has the biggest evidence? Log evidence. And we're not talking in absolute value, right? We take logs because it's easy. So which model has the maximum evidence? This is minus 18, minus 20, and minus 21. So which one? The first one. And you can actually see when you go and you compute the posterior over models, and you can do this calculation actually in one line, and we will do this when we discuss regression. The posterior over models, for model 1 it comes to be the maximum, model 2 the second highest, and model 3 very small. So this Bayesian setting immediately tells you for this particular data set, with like 1, 2, 3, 4, 5 points, the straight line best explains the data based on the evidence calculation. Now, if you repeat the same problem with more data, you notice that the evidence here is minus 106, minus 103, and minus 108. So the maximum evidence is for the quadratic, and you can see when you calculate the posterior over models, you get a huge value. I mean, don't try to guess, right? Looking at this and say, oh yeah, this is better. No, because this is the formal way. Look at this. You calculate the probability and it's huge. So you know that fitting a quadratic to this case is the way to go. Now, this computer program, and I think this is from Murphy's toolbox. The previous calculation, I had another little program, is from Zubin Garamani's paper. Calculating the evidence for these linear regression models, the program is about 30 lines of a code. But there is an equation that you have to calculate the evidence, and you have to put the evidence explicitly, right, with particular prior models and, you know, doing the calculations. So you have to do the calculation of the evidence and the posterior analytically, but once you have it, calculating this is trivial. Okay? So when we discuss regression, I'm going to come back to tell you on how we do this calculation. Okay. This is a repeat. There is nothing new here, so I am not going to bother. So I mentioned that when we calculate the evidence, it comes to be the ratio of marginalizing factors. Okay? So we have 6 minutes left. So let me give you a very general formula that you can use it for any problem. Any algorithm, anything that you need to calculate the evidence. Can somebody remind me, how does a beta distribution looks like, let's say with parameters A and B? What's the definition of a beta distribution, let's say for theta? Is θ theta to alpha minus 1, 1 minus theta to beta minus 1, divided by what? To normalize it? By a beta function with parameters a and b. Okay? So, in writing every distribution, let's say, over parameters, you have some functions of the parameters, like theta to some power, 1 minus theta, another power. You have some functions of the parameters, and then you have some normalization constant. Some normalization constant that does not depend on theta. So what I'm going to do is, I'm going to take the prior, and I'm going to write it as some function of the parameters theta, divided by the normalization factor of the prior, that I call it Z0. All right? Okay, so remember Z0 is the normalization factor of the light. I am going to take the likelihood, and I'm going to write it some function of theta divided by ZL, where ZL is the normalization factor that I get from the likelihood. All right? A normalization factor that I get from the likelihood. And here is, and of course, we have the posterior. So the posterior will be some function of theta divided by normalization factor of the posterior, and I call it Zn. N is the number of data points that I got, right? So Zn is the normalization factor. It's a constant that normalizes the posterior. So let's look at this trivial calculation. The posterior is the likelihood times the prior divided by the marginal likelihood. And we want to calculate this marginal likelihood. This is, to do model selection, we need to calculate P of D. So I write the posterior as some function of theta divided by a normalization factor. I write the prior as some function of theta divided by a normalization factor. And I write the likelihood as some function of theta divided by a normalization factor for the likelihood times P of D. Now, if you have a function of theta here, where is it? A function of theta, and another function of theta, and another function of theta, what happens to this on the left and the right hand side? They better cancel out. Right? If they cancel out and you solve for this marginal likelihood, what do you get? That the marginal likelihood is the ratio of the normalization factor of the posterior divided by the normalization factor of the prior times the normalization factor of the likelihood. This formula, you can use it all the time, assuming you can actually look at the books or at Wikipedia for the different distributions you use, and you say, what's the normalization factor for a Gaussian? What's the normalization factor for a beta distribution? And what likelihood do I have? Compute that, and this formula is extremely powerful. So the plots that I gave you before for regression, right? Effectively what you do is, once you have a prior model and you calculate the posterior, you compute these normalization factors, and the log of this is what was plotted on the previous diagrams. And we will do these calculations again in the regression lectures. So let me, 2 minutes to go. So let me do this example for the toin cost, the coin problem, where we're going to assume that the likelihood is binomial. So in n tosses of the coin, I get n1 heads and 0 tails. We assume that the prior is a beta distribution that you see here. All right? And you remember when you multiply the binomial with a beta distribution because they are conjugate to each other, right? The prior that you use here, the beta is conjugate to the binomial. You get a posterior that is also a beta distribution. So the final answer for the marginal likelihood comes to be this wonderful formula. So what is B of A, B? From where is that coming from? The normalization factor of the prior. Where is this thing on the numerator comes? Is the normalization factor of what? The posterior. All right? And where is this factorial of n given n1 comes? That's the factorization of the likelihood. That's the constant term, the normalization factor in the likelihood for the binomial distribution. So again, the model evidence for this case is given by this wonderful formula. It's 1:46. I am going to stop there before the light goes on. But when we come back, I'm going to show you a more interesting example. If your model is the multivariate Gaussian, and you use a normal inverse wizard as a prior for the mean and the variance, how do you calculate the model evidence? And the model evidence comes this wonderful formula using the multivariate gamma function. And so please look in Murphy's book for a review of this inverse wizard distribution.
Existing above 0, 30% of the mass is existing below 0. And I guess these blue lines are indicating, yeah, so these blue lines are.
All right, so we need to continue this general discussion on model selection. And I remind you, one of the things that we use is this marginal likelihood that you see here. If I can make my pointer to work. So this is the marginal likelihood for a given model. And so that's the denominator in the Bayes rule, right? And it's essential for model selection. And I gave you a general trick, if you like, on how to compute it using normalizing factors. So can somebody remind me what this Z0 is the normalizing factor of? Of the prior. ZL is the normalizing factor of the likelihood, and Zn for n measurements is the normalizing factor of the posterior. So this is actually a very powerful way to compute this marginal likelihood and to select models, but I can tell you that these normalizing factors, as you expect, they're very complicated functions of different parameters. So right now we list them, but what you do with them in the context of model selection, it's another story. So there is a lot of algebra involved in doing this type of calculations. All right, so I have an example here that to appreciate means you should know things about Gaussians. And there is a chapter both in Murphy's book and in Bishop's book. If you think you know everything about Gaussians, the answer is you don't. Okay? You just don't. But I cannot spend time to tell you everything about Gaussians, right? So I am assuming when you try to understand this slide, you go and you look and you understand what's going on. So what we have here is we have a multivariate Gaussian to be our likelihood model. All right, so you know what a Gaussian is in d dimensions. So that's my likelihood model. So when it comes to ZL, all right, this could be the normalizing factor when I take n measurements from a d-dimensional Gaussian. So from everything you see on the right-hand side, can you tell me which term comes to be the normalization factor of this d-dimensional Gaussian? So I have a very complicated expression here. Which term is the normalizing factor of the d-dimensional Gaussian? Take a Gaussian, everything that involves the mean, the variance, those things will cancel out, right, as we discussed in the previous lecture. So you need to keep only the normalizing terms. So which ones are those? And I have n measurements. Right? Now what I would do is, if I was you and I have my computer in front of me, I'm going to go to Wikipedia and say multivariate Gaussian, rather than just looking at me. And when you say multivariate Gaussian, you look and you tell me what is the normalizing factor. What do you think?
Pi to the power ND.
So 1 over 2 pi, all right,
Yeah,
to a power d over 2, to a power n, because I have n measurements. That's it. Okay. So in this model, of this multivariate Gaussian, I'm going to take that both the mean and the variance are unknowns. So these are my parameters. So what I will need to do is I'm going to need to put a prior, and the prior that you put on simultaneously on the mean and the variance is what is called a normal inverse Wizard distribution. Okay? And your antennas may be going up, and you say, what is that? So what I did is I cut and pasted the equation for a normal inverse Wizard distribution on the mean and the variance. It has 4 parameters. And I'm going to simply tell you what it is. Given sigma, it's a Gaussian distribution. If I knew sigma, so the conditional is a Gaussian distribution with these parameters. And then the distribution on sigma, if you use the product rule, is an inverse Wizard distribution. That's why we call this a normal inverse Wizard distribution. And so this is the Gaussian, all right? Okay, so you can see, I can see at least the fundamental parts of the Gaussian, okay? And you don't see the normalization factor because the normalization factor that you see is for the total distribution for the normal inverse Wizard. So that Z there is the normalization factor. And you see here from this inverse Wizard distribution on sigma, you have this, this interesting term here, okay? And the determinant of sigma to this power. Now, obviously, you may not have seen this before. So what is an inverse Wizard distribution on sigma, right? Sigma is a matrix, right? It's a d by t matrix, and it's a symmetric positive definite matrix. So the inverse Wizard distribution is a distribution over symmetric positive definite matrices. Sounds a lot of there, right? But it is a distribution over, so if you take a sample, every sample from this distribution is a symmetric positive definite matrix because this covariance matrix has to be symmetric and positive definite. Okay? So on the bottom, again, Wikipedia, this is the normalization factor of the normal inverse Wizard distribution. S0 is a metric, so this is a determinant. This is the d-dimensional gamma function. And the rest are the coefficients, basically the parameters that you use in mu0, k0, s0, and nu0. So if you look on the top, if I look actually on the bottom, can you guess, looking at this equation on the bottom, right? That's the normalization factor for the normal inverse Wizard distribution. What is this thing on the denominator? Is the normalization factor of which distribution? Right? I'm just following the formula. So this is the normalization factor of which distribution? Of? You have no energy. If you don't have any energy, I'm going to be losing my energy prematurely. I still have time to go. So what is that factor? Is the normalization factor for what distribution? You remember ZL is the normalization factor of the likelihood, which was Gaussian. That was it. Z0 is the normalization factor for the prior, and we said the prior would be normal inverse Wizard, and I can see the normalization factor for a normal inverse Wizard. So this thing on the denominator is what? Is the normalization factor of? Of what distribution?
Prior.
Of the prior, thank you. And obviously I'm not proving it here, but if you read the review chapters, both in Murphy's or in Bishop's book, you will see that when you take a likelihood that is a multivariate Gaussian, and you take for the mean and the variance a prior that is normal inverse Wizard, that is a conjugate prior, which means the posterior is also going to be a normal inverse Wizard. So nu subscript nu and k subscript n, etc., are the parameters, the updated parameters for the posterior. And I'm not giving you the exact expressions for them, but I mean, I can guess. For example, nu most probably is nu 0 plus n, which makes me wonder why there nu 0 plus n I should have put nu subscript capital N, all right? But, you know, if you look at the slide carefully, you will figure out, okay? So this is the normalization factor of the posterior that looks identical to the normalization factor of the prior, but you have updated the parameters from nu 0, S0 to Sn, nu n, etc., Kn, etc. And somehow I cut it, all these update formulas for nu n and Kn, etc., because this slide actually was part of my lecture from the earlier course. Okay, so I don't know if you heard about these things last fall, but so that's what we have. So this formula that you see here, it's extremely powerful, right? So you have a way to calculate this marginal likelihood, and the marginal likelihood, the evidence, is what you need to be able to do model selection. Okay. By the way, I'm going to come back to this when we start doing regression in fine detail, starting from scratch. You will see these formulas again with little toy and a little bit also more complicated examples. So now what I want to do is I want to discuss about a very powerful concept, an extremely useful concept, which is called the Laplace approximation. Anybody knows the Laplace approximation? Have you heard this in your previous course? You did? All right, so you remember? All right, so I am going to use the Laplace approximation to actually approximate this marginal likelihood, the model evidence, but obviously this Laplace approximation is way more powerful, right? So what's the idea? If you have a very complicated posterior in many dimensions, you assume that it's sort of narrow, you know, because you have lots of data, and it picks around the map estimate, and maybe looks like a Gaussian. And if it looks like a Gaussian, you make it to be a Gaussian. That's the Laplace approximation. So people in all areas of machine learning, including deep learning, when you want to calculate, do Bayesian calculations and find, let's say, the posteriors of the weights or something like that, the Laplace approximation is an easy way to get out of this problem. Doesn't mean it's good or anything, right? It's an approximation, and so if you use it at your own risk, but it's an approximation that if there is nothing else to do, Laplace approximation. Okay? So I will not feel bad about it. All right, so I am going to knock derivations because, again, this is part of an earlier course, but I'm going to remind you what the formula looks like. So let me, I'm going to look at the equation on the bottom. So don't bother about this calligraphic M. So this is model M that has these parameters theta M. I have data D, so this is the posterior of the parameters of this model. So I want to have a Gaussian approximation of the posterior of these parameters. So what I'm going to do is I'm going to assume that I know the map estimate, right? So we have found the theta M that maximizes this distribution. And I'm going to go and fit on the top of that map estimate, all right? I'm going to fit a Gaussian distribution. So the way we're going to do it is, I want you not to look at that slide, but I want you to imagine a Taylor series expansion, including the constant, the first and the second term, for the log of this posterior. So let's do it together, all right? So we're going to do a Taylor series expansion of the log of the posterior around the map estimate. So what's the first term when you do Taylor series expansion? What do you get? You get some constant. And then the second term, what is it? Is the derivative times theta minus theta map. Right? And what is the derivative at the map point of the log of the posterior? 0. Why 0? By definition, right? Because at the map estimate, the posterior is maximized. So what you left is a quadratic term that is 1/2 theta minus theta map. And what is this thing that I'm going to put there? Is the second derivatives of the log of the posterior. And because I see there is a minus sign there to make it to look like a Gaussian, obviously I'm going to take A to be minus the second derivative of the log of the posterior. Everybody can see this? So basically, once you extract this term, there is no linear term, the posterior will look like proportional to this, which you immediately recognize as a Gaussian. So the only thing you need to add is the normalization factor of the Gaussian. Okay? Which is, you see here. So this will have come from the constant term, if you like, when you do Taylor series expansion, but you don't write it, oh, the log of this plus this, etc. No, you say something constant plus this quadratic term, then you say the distribution will be proportional to this exponential. So obviously this is Gaussian. So what's the normalization factor of a Gaussian? It's this, done. That's the Laplace approximation. Okay? Extremely powerful. If you have a posterior and there is no way to do much with it, so if you need to take samples from it and you cannot, if you want, I don't know, to use, let's say, this posterior to maybe to calculate the predictive distribution, right? You remember the predictive distribution is an integral of the likelihood times the posterior integrator of the parameters. You say that integral is so complicated, I cannot do it. But if you put a Gaussian, and the likelihood, let's say, happens to be a Gaussian, you know the answer exactly, because it will come to be the normalization factor of some Gaussian. Okay, so this slide on its own, right, what you see on the bottom, it's extremely important, and we will use it in different topics in the course. But now what I want to do is, because we talk about model evidence, I want to compute, rather than using this exact formula that I gave you, right? This is the exact formula. Come on. All right, so this is the exact formula in terms of the ratios of these normalization factors that they look very complicated. So what I want to do is, I want to use the Laplace approximation and see if we can get the model evidence approximated when the posterior is computed through the Laplace approximation. So let's see the algebra. Look at this equation, by the way. Don't bother with this calligraphic M, so you can completely forget that there is a calligraphic M. Calligraphic M means this is for model M, right? And I'm putting it there because we only compute the model evidence to compare different models. But if you look for this model M, so what you have is, you can see here, this is the posterior on the denominator, and the posterior is the likelihood times the prior divided by the marginal likelihood. So the marginal likelihood will be the likelihood times the prior divided by the posterior. So what I'm going to do is, we have an approximation for the posterior using the Laplace formula. So I'm going to take logs of this equation, all right, and I'm going to compute every term on the right-hand side at the theta map estimate. So let's see, I have the log of the evidence, so I'm going to have the log of the likelihood where the parameters are fixed at the map estimate. I have the log of the prior, and what is the rest of the terms? From where are they coming? The Laplace approximation, right, is the log of that Gaussian that approximates the posterior of the parameters. All right? So let's continue. So we have the log of the likelihood where the parameters are fixed at the map estimate, the log of the prior computed at theta map, and somehow I dropped the quadratic term. Why? Because I said I am going to approximate the right-hand side at what value of theta? At the map estimate. And at the map estimate, this is 0. All right? So there is a very general formula, actually quite easy to, if you think about it, right? This is the likelihood with fixed parameters. This is the prior computed at the map estimate. And A, what is A, remind me? Is the second derivative of the log of the posterior. okay, computed at the map estimate. All right, so maybe we need to do something about log of A because it may be nasty, right? I mean, second derivative of the log of the posterior, okay? So that may not be so easy to work with. So we have to do something. But I want you to sort of immediately appreciate that the log of the marginal likelihood that we use for model selection is not just the likelihood term, right? So it's like to find the best model, you don't maximize the likelihood because this will give you a very complex model. And you notice here there is a minus log of the determinant of A. So this looks to me like a penalization term that eventually may be saying, but be sure the model is not very complex. It's not clear yet, right? But there is a minus sign there that obviously penalizes the likelihood to give us the marginal likelihood. All right. So let me continue. Approximations. I'm going to take now this formula we derive the case of n going to infinity. So we are going to assume that we have lots of data. All right? And lots of data is relative, so it doesn't have to be a million data points, but we have sufficient data. Can you tell me the log of the likelihood, how does it vary with n? So, I collect one data point and another, I collect n data points. So as a function of n, how does the log of the likelihood vary? I mean, we have seen lots of examples on this, right? So how does the log of the likelihood vary? I mean, let's say if the likelihood is a Gaussian, right? So you get the likelihood of 1 point, there's a Gaussian, another data point, you're going to have the Gaussian square, the Gaussian cube, etc. So how does it vary with n? The log of the likelihood. Does it vary linearly, quadratically, logarithmically? What does it vary? So if you have something to the power n and you take the logs, linear. So if the likelihood varies linear with n, the log of the posterior will vary linear. Which means I can actually do the following. I can say that as n grows, going to infinity, A grows as n times A0, where A0 is some fixed matrix. Can you see that? Right? N, remember, is this minus the second derivative of the log of the posterior. So the log of the posterior varies linearly with n, all right? Which means A grows as n times some fixed matrix A0, and we don't really care what A0 is, because constant, okay? All right, so let's compute the log of the determinant of A. The determinant of A would be n times A0. So effectively, everything is multiplied by n, so this determinant is going to be n to the dimension of our parameter space, n to the power d times the determinant of A0. So if you take the logs of this, you get d times log of n, and a log of some constant determinant there. So as n goes to infinity, the log of the determinant of A becomes d times log of n. This is extremely powerful result. Okay? So the log of the determinant of A, all right, becomes d times log of n. So if I plug in this in there, really I don't have to keep this because, as n goes to infinity, this is a small number. I don't really have to keep this because it does not grow with n. The likelihood obviously grows with n. So this is what I get. I get the following approximation for the log of the this marginal likelihood to be the log of the likelihood computed, the parameters computed at the map estimate, minus 1/2 of log of A, the determinant of A, which is d times log of n. And we're done. What you see there is what is called the Bayesian information criterion that is used to approximate the evidence, and it's derived in a fully Bayesian setting using the Laplace approximation. in one slide. All right? So in one slide, we have been able to derive the Bayesian information criterion, the BIC, okay, that says, look, you're going to select a model that maximizes the evidence, but the evidence is not just maximizing the likelihood that overfits, but also penalizing the complexity of the model. And the complexity factor here is d over 2 times log of n, right? D over 2 times log of n. So this is really a Bayesian criterion because everything we derive follow the Bayesian formulas. And it's very nice because, you know, it's very straightforward to compute, right? In one line, this is the likelihood, so the only thing you need is the map estimate. And I can even tell you the good news, lots of people don't even use the map estimate. Once they understand where the complexity penalty comes, instead of the map estimate, they use the MLE estimate. And they say that's, you know, because the MLE is very easy to get by maximizing the likelihood. So instead of having the map estimate, they use the MLE estimate. All right. Now, a few observations, actually. This next slide is the same as this one. So let me just mention them with this slide. So D is the number of parameters in your problem, right? Because we computed posterior, there was a D-dimensional posterior. Later on, when we start doing some serious problems, we will see that D is not really all the parameters, but only the effective parameters that can be computed from the data. Because some parameters, whatever you do, you cannot compute them. So in general, I want you to remember for now that D is sort of the effective parameters that can be computed from the data. So later when we do, you know, when we try to use, let's say what's called relevance determination to find how many parameters we need, there we're going to discuss about the effective parameters, and this is what this is going to be about. But right now, you know, this is the number of parameters in the problem, and later on maybe we will simply you know, modify this a little bit. I know I have not said anything about you know, regression yet, right? Except in the introductory lecture. But you know, in machine learning, unfortunately, and I have discussed this with many people, is not, you know, you read page 1, you learn the essentials, so you keep going and you add things. Because chapter 1 on one book requires chapter 25, and chapter 2 requires chapter 36 in another book, okay, unfortunately. So what I want you is, because we're talking about this big criterion, I wanted, just in case we forget about doing this when we discuss about regression, to apply to a simple regression problem. Even though regression is a lecture that is going to start coming up, if not tomorrow, next week. So let me just remind you what we're going to do with regression, okay? Nothing essential. We're going to have some input X, and I'm going to provide you for some training data X, some responses Y, and then we're going to try to fit them to some Gaussian model that for each X, it gives us the response Y, that's going to be a Gaussian with some noise sigma, all right? So some standard deviation plus minus sigma. So the unknown parameters on this regression problem that we will need to compute from the training data will be this parameters W that determine the mean response at X, and also the noise sigma square. I mean, that's what linear regression is going to be. Plus many other good things, but you know. So for this problem, did you talk in your previous class about how to compute maximum likelihood and all of this? You did? All right. So again, we will see all of these things, but I can tell you, if you try to compute the maximum likelihood estimate for this problem, for the parameters W, you get actually the least squares estimate. And again, it's completely unimportant right now, but this is what W bar is the maximum likelihood estimate. And for the noise, the maximum likelihood estimate, so the estimate that maximizes the likelihood, is the empirical variance actually. You can see this is the error that you do, and I forgot here to put a square, all right? So there's a square there missing. So the error that I do on the training data, all right? So my model says the answer is W transpose Xi, where this W is the MLE estimate, but my measurement saying the actual value is Yi. So this empirical error defines the MLE of the variance. All right. So I'm going to give you a formula to compute the marginal likelihood for this regression problem using the big formula that we saw in the earlier slide. So the first thing we need to do is I am going to use the MLE estimate rather than the map estimate and compute the likelihood, the log likelihood. You remember the marginal likelihood, it was the log likelihood minus this penalization term. So can somebody tell me where this thing came from? Where is the second line came from? It's log, right? I'm taking the log of the likelihood. So where is this thing came from? Yeah, it's basically the sum of Gaussians, right? And so it's for each data point, my likelihood is a Gaussian. So when I take the log of this, I'm going to get n times the normalization factor, and then I'm going to have summation over my data points divided by 2 sigma squared that you have in your Gaussian. That's it. Okay, and I'm going to compute my point my sigma and W using the MLE estimates that we have not derived them, but I give them to you on the top. Okay? So you can rewrite this minus n over 2 log of this, and then I have this square, and again this is supposed to be squared here, the parenthesis. So you can see the square term is n times sigma squared. So this last term becomes n over 2, and here is the final approximation, the big approximation for the marginal likelihood for my simple trivial linear regression problem. It says the marginal likelihood, all right, or the log of the marginal likelihood is minus n over 2 log of 2 pi sigma squared minus n over 2 minus d over 2 log of n. All right? That's it. We're done. I mean, how do you like this as an approximation of the marginal likelihood without having to compute any integrals, any normalization factors? There it is. So actually when you try, if you look at different examples in, let's say, Murphy's book or other machine learning textbooks, you may see weird long formulas, not as simple as this. And you may get these and you say, what is this, from where it's coming? So you better know from where it's coming. You're going to have to do the algebra on your own. But what's the algebra? It's very simple. Whatever likelihood model you have, compute the MLE so you don't bother with the map. Take the log of the likelihood, subtract the penalization term that we computed, d over 2 log of n, and you're done. All right, so that's the big estimate. And later, when we do regression, I will be asking you to evaluate which model is best, and I'm going to give you many models, and you're going to have to compare the big estimate of the marginal likelihood and plot this and make decisions based on that. All right. Sometimes, if you are trying to find the best model, right? So you have to maximize. In some books, they like minimization problems. So instead of using the big, they use minus some factor of the big, and this is what they use. They call this the big cost, which is minus 2 times the log of the marginal likelihood. So if you multiply the previous results with minus 2, you get for our regression problem, something like that, and then you have to minimize, when you compare models, you can look at this as a minimization problem. But nothing really of, I wouldn't even bother for you to remember this, but it's on the slide, so I'm just telling you. Now, I think on the introductory slide, I mentioned something about overfitting and the need to penalize complexity of the model, and we will see this in fine detail when we discuss regression. But I think I'm almost certain that I had plotted, I had given you the formula for what is called the Occam information criterion, which looks like the log of the likelihood computed at the MLE, okay, minus the number of parameters theta m. So this is what I gave you in the first lecture. So this, if you look in many machine books and in statistics, you will come up, and if you search on the web about this Occam information criterion, and you notice here it says minus the degrees of freedom, so minus d. And I remind you, what did we have here in the Bayesian way? It was minus d over 2 times what? Log of what?
N.
Log of n. So the only thing I'm going to say, this Occam information criterion is not Bayesian. It's heuristic. All right? It's heuristic because the person who invented it said, we really have to control the complexity, so put minus how many parameters I have in my problem, so this number of parameters doesn't explode. But there was no derivation from any sort of methodology that follows the Bayesian setting. All right, so it was fully sort of empirical, certainly non-Bayesian. And can you tell me which model penalizes more for complexity, this or our big criterion? Just looking on D alone, so here it says minus the number of parameters D. The other one was minus D over 2 log of n. So which model penalizes more? Is this penalty, okay, I have both of them, which penalty is more severe, this or that?
Depends on the number of data.
Well, let's consider the case even of lots of data.
The BIC.
So the BIC does what?
That's the one who penalized the most.
So if it penalizes the more, so the BIC will give you simple models. All right? So if you use the Occam information criterion, we'll give you models that are a little bit more complex. And somehow, because of that, many practitioners in machine learning, they prefer it because they say this concept of having everything so trivial and so simple is just not very appealing. They like to have some complexity so things look nice when you write papers. All right? But I'm just saying this derivation here of the Occam information criterion, there is no mathematical formalism, it's not Bayesian, it's fully empirical, okay? So I really, in today's world, this is the way to actually work if you need to use an approximation of the marginal likelihood. Okay. So let me philosophize now a little bit, and this will come many times in the course. So I remind you that the marginal likelihood, right, is the denominator in the Bayes rule when we write the posterior for the parameters, right? So the posterior of theta given the data is the prior times the likelihood divided by the marginal likelihood P of D. So P of D was an integral of the likelihood times the prior integral over the parameters. So if somebody asks you, where is the prior plays the most important role? The answer is in the calculation of the marginal likelihood. So when you calculate the posterior of the parameters, right, it is very possible the effect of the prior, if you have lots of data, is negligible, it doesn't do anything. But when it comes to the calculation of the marginal likelihood, the effect of the prior is felt significant. For right? Because you remember the marginal likelihood is not the integral of the likelihood times the posterior, it's the integral of the likelihood times the prior, right? So, so we may, my next lecture is gonna be on the selection of the priors to give you at least some flavor on that topic before we move to supervised learning. But somebody will say, so the marginal likelihood will come to be incorrect if I use whatever prior comes to my head. So how do I fix this problem? And that leads to an extremely powerful concept in machine learning that we will spend at least one full lecture on the topic, but I want you to actually get it now. So when it comes to different applications, I can throw an equation here and there. So you remember what is so I have model M, all right? So forget this M, all right? So this is for model M, so the marginal likelihood, you remember it was the likelihood times the prior. But now I have done something extra for this prior. So the prior is actually from there to there. What is the extra thing that I have done? I said the effect of the prior on the parameters, let's say W, it's important when I calculate the marginal likelihood. So how about if I allow some hyperparameters in the prior and I put a prior on the prior parameters? So basically, let's say the prior is a Gaussian, right? So let's say the prior on W, I take it as a Gaussian. That's what we will do when we discuss regression problems. So we take the prior on W to be a Gaussian. So the Gaussian has an unknown mean and variance. So what I'm going to do is I'm going to put a prior on that mean and variance. And you're going to say then, and what is the effect on the prior of this prior on this hyperparameters alpha? The only thing I can say, the effect on alpha is less significant than the effect of W. In other ways, when I keep putting a prior on the prior on the prior, etc., as I do it hierarchically, the effect of this hyperparameters alpha diminishes. All right? So in other ways, I'm diffusing the effect of the prior by putting a prior on the hyperparameters. Now, you may say, fine, good. You compute the marginal likelihood now having an integral that involves, instead of one, the prior of W, you have the prior of W given alpha, and another prior on alpha, and then, of course, you have to integrate all the parameters, right, to compute the marginal likelihood. So the integral has to be on W and alpha. So you make your life miserable. So what's the answer to that problem? That is, I will say, it takes place in about 90% of the machine learning algorithms. So we need this. So we're going to do this. But we cannot afford computing these high-dimensional integrals. So what's the idea? All right. So since you haven't done this before, so let me just go directly on the answer, and I'm looking only on the equation. Since the effects of this hyperparameters alpha, okay, is less important than the prior on W, I am going to take a point estimate of alpha. So I am not going to do an integration at alpha. I'm going to take a fixed value. But that fixed value, I'm going to compute it by solving an optimization problem. And that optimization problem is going to maximize my marginal likelihood that if you look at it carefully, that's my marginal likelihood the way we looked before, but because there is an alpha there, it's a function of alpha. So we're going to maximize this by finding a point estimate alpha, and that point estimate is going to be used to compute my marginal likelihood. And that methodology goes with the name Empirical Bayes, which some people can confuse the names, and sometimes the names have been introduced, right, for good or bad reasons, and maybe without too much thought about it. But Empirical Bayes, basically, it's a way to approximate these integrals that we had before, where you compute the marginal likelihood by having the hyperparameters compute it as a point estimate, and that point estimate maximizes the marginal likelihood, right? So in some sense, I called this the marginal likelihood before. This thing here is also the marginal likelihood, right? As a function of alpha. Can you see it? As a matter of fact, I call this the evidence, but if you look carefully in the literature, let's say when they use empirical Bayes, the evidence actually that they use is this marginal likelihood that's a function of hyperparameters. All right, so I want you to sort of adjust the terminology as you go along, trying to have an understanding of what we are talking, okay? So, certainly this is a marginal likelihood where all the parameters have been integrated. There's no parameters here, all right? This is a marginal likelihood where W has been integrated out, but the hyperparameters are still there. And so when people talk about the evidence approximation, and there is a homework problem that I gave last year, and I'm going to give you the same thing this year. The evidence approximation is actually to compute this integral, and then find the alpha that maximizes this integral, and then plug it in, that alpha in here, to do model selection. So today we have seen already some very powerful concepts, right? The Laplace transform, the Laplace approximation, the Laplace transform, the Laplace approximation, using the Laplace approximation to get the big estimate for the marginal likelihood. And then we have seen this new concept of using this empirical Bayes to reduce the effect of the prior in computing the marginal likelihood and doing model selection.